Hey guys, welcome to video number 25. I thought today would be a good idea to talk about gain, logarithms, and decibels. So in the upper left hand side of this page we've got the block diagram symbol for some generic circuit function. Could be an amplifier, a filter, a comparator, a differentiator, just about anything you can think of. Now if we were dealing specifically with an amplifier, we'd probably use this triangular symbol. And one of the main characteristics that we'd be interested in would be its gain, that is, its output divided by its input. Now, up to this point, we've seen three different kinds of gains: voltage gain, current gain, and power gain. I put voltage gain first because that's the easiest one to work with and measure in real life. We could use an oscilloscope to measure V out and V in to get this ratio, or sometimes we could even just use a DMM. Now, current is a little bit less convenient to measure, so we're not going to work with current gain directly that often. And power is even harder to measure, so power gain is the worst of these to try and measure directly. Fortunately for us, though, power gain is the product of voltage gain and current gain. Now that comes from the fact that power equals V times I. All right, now let's come back to this block diagram symbol and assume that we have an amplifier represented by this thing. So if I expand it a little bit, I come down here, I see that the input resistance of the amplifier is what this source thinks it's driving, and that produces an output voltage equal to AV, the voltage gain, times V in. This diamond-shaped symbol is a voltage-controlled voltage source, and that's analogous to the current-controlled current source we used when we developed models for the bipolar transistor earlier. All right, we'll come back to this in a minute, but first what I'd like to do is develop a definition of the decibel. All right, the decibel is a logarithmic measure of a power ratio, and normally we're dealing with power gain, which is power out over power in. We're going to work with base 10 or common logarithms, which I'll write as log of x, as opposed to natural logarithms, which I'll write as ln of x. The basic unit of logarithmic power gain is the bel, and that's defined as the base 10 log of power out over power in. We don't use bels very often, but we do use decibels, and the decibel gain is defined as 10 times the base 10 log of power out over power in. Now, coincidentally, as I was making this video, I happened to hover my mouse pointer down here, and look what popped up. It's Alexander Graham Bell Day, and there he is in all of his glory. And that's who the decibel and the bel are named after. Although we only use one bel when we use the unit bel, it is named after Alexander Graham Bell. So, pretty interesting coincidence. All right, now let's just do a couple examples to solidify this information. Here I've got an amplifier driving a loudspeaker, and in order to produce a 10-watt power output, we have to absorb 10 microwatts from this source. So the power gain, I'll call A sub P, which is power out over power in, is equal to 10 watts divided by 10 microwatts, and that's 1 million. All right, the power gain in decibels, I'll call that AP dB, is equal to 10 times the log of 1 million, which equals 60 dB. All right, so this amplifier has a power gain of 60 decibels. Now, underneath it, I've got an attenuator, and an attenuator just produces a smaller output than it has as an input. In this case, it outputs 0.5 watts with 5 watts input. So its power gain in decibels is equal to 10 times the log of 0.5 watts divided by 5 watts, which equals 10 times the log of 0.1, which is minus 10 dB. So this attenuator has a gain of minus 10 dB. Now we could also say it has a loss of positive 10 dB. So it's a matter of semantics, okay? That the gain equals negative 10 dB and its loss is equal to positive 10 dB. All right, sometimes that can cause a little confusion, but you know, hopefully that makes it clear. All right, now what I'd like to do next is develop an equation for the power gain in decibels in terms of the voltage gain. All right, so we're going to work with this amplifier, and we know that the voltage gain is V out over V in, and of course from Ohm's law we know that power equals V squared over R. All right, so coming over to the input, the power delivered by the input source, P in, is equal to V in squared over R in, and the power delivered to the load is V out squared over RL. And power gain, A sub P, is equal to power out over power in. All right, so power out is V out squared over RL. And power in is V in squared over R in, but rather than divide by this, I'm going to multiply by the reciprocal, so that's R in over V in squared. All right, now, one of the assumptions we always make when we're working with decibel voltage gain is that RL equals R in. Okay, now that's almost never true in real life, but it's always the assumption that's made when we're working with decibels. So if that is the case, then these cancel and we get the power gain is equal to V out squared over V in squared, which we can write as V out over V in the quantity squared. All right, and to express this in decibels, AP in decibels is equal to 10 times the log of the power gain, which is V out over V in squared. But the rules of logarithms tell us that we can bring this exponent down and multiply this coefficient, which gives us the power gain as 20 times the log of V out over V in, or equivalently 20 times the log of the voltage gain AV. So these are our power gains expressed in terms of the voltage gain. And if you've ever wondered where that 20 comes from, that's it. All right, now let's do one more example here, and let's look at the filter circuit that we had at the end of the previous video. If you recall, that filter had a corner or cutoff frequency of 1061 hertz, and one of the inputs we evaluated it for was 10 sine 2 pi 1000 t, which is 10 volts peak, 1 kilohertz. And that produced an output of 7.3 volts, lagging by 43 degrees. All right, now when we're determining the response of this filter in decibels, we don't care about all this instantaneous trigonometric stuff. All we really care about is the peak or RMS values, if you prefer. So for this filter at 1 kilohertz, its response, which we'll label as H, right? Remember, when we're dealing with filters, very often we use H to represent its gain. So H in decibels is equal to 20 times the log of V out over V in. All right, so we've got 20 log 7.3 volts divided by 10 volts, which is 20 times the log of 0.73. And let's call up our calculator here, and we've got 0.73. We take the log base 10 times 20, and we've got a response or gain of about negative 2.73 dB. Negative 2.73 decibels. So the response of this filter, that is the gain of this filter at 1 kilohertz, is minus 2.73 decibels. All right, we'll come back and look at more of this stuff in the next video. We're going to jump back into filter analysis stuff. But that's all I have for you today. So happy Alexander Graham Bell Day to you, and I will see you next time.